Recording in progress.
As chair of IEEE CSS RES Joint Chapter, I take great pride in welcoming all the attendees of the 2021 International Conference on Mechatronics, Robotics, and System Engineering, especially for our honorable and distinguished keynote speakers, Professor J. Katupitia from University of New South Wales, and Professor Maki Habib from the American University in Cairo, and Dr. Nico Saputro as the General Chair and all the committee as well. We are delighted to have you among us. On behalf of IEEE and committee, we would like to extend our warmest welcome and good wishes. Welcome to the IEEE publication through morse 2021. A non-for-profit organization, Institute of Electrical and Electronics Engineer, is the world's largest technical professional organization dedicated to advancing technological innovation and excellence for the benefit of humanity. As the largest publisher, we have to keep the quality of the accepted papers before the submission to the IEEE Explore. As soon as this conference is over, we sincerely request and expect all participants to immediately re-examine and revise their papers, both based on reviewer comments in the letter of acceptance and audience comments in today's parallel session. Before submitting to IEEE Explore, we, from the IEEE CSS RES Joint Chapter team, will review the compiled papers one by one. If the authors do not revise it properly, we will review it again and return it to the committee. The committee will return it to the authors and vice versa. Of course, this process will increase the time for your paper to be published. If we do the review process again, there will be most likely additional comments. If you don't want to get additional comments, please immediately revise them carefully, accurately, and correctly. Generally, the eye-catching errors are overall format, image quality, and technical problems can also be found in English quality, the structure of the paper, such as numerical results in the abstract and conclusion, literature supports from currently published paper from reputable journal, clarity and regularity of writing methods, and quality of discussion. I hope that the things I have mentioned above will be re-examined more carefully by both authors and committee. If we are able to follow all the instructions, usually the paper will be published less than 1 month after the submission to the IEEE Explore. Most recently, in the last August, papers from Universitas Prima Indonesia were published within 10 days after the submission. Once again, thank you for the hard work of the committee so far, and especially the review process after the conference. Chair of IEEE Indonesia CSS RES Joint Chapter, Arjon Turnip, PhD.
And now we would like as well to invite Vice Chair of IEEE Indonesia section to give his remarks. Let us welcome Professor Gamantio Hendra Toro.
Thank you. Dear distinguished guests, colleagues, researchers, professionals, students, ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Prosperous and warm greetings to all of you. First of all, I would like to thank the chair of the committee for the 2021 International Conference on Mechatronics, Robotics, and System Engineering, morse 2021, for inviting the chair of IEEE Indonesia section to give a few words at the opening of this conference. On this occasion, I am speaking here on behalf of the chair of the IEEE Indonesia, as he could not attend this conference today due to other commitments. the honorable speakers, Professor J. Katupitia and Professor Maki Habib, the Honorable Dean of the Faculty of Industrial Technology of Parayangan Catholic University as the host of the conference, the Chair of IEEE Indonesia Control System Society and Robotics and Automation Society Joint Chapter, the General Chair of Morse 2021, as well as all participants. On behalf of the Chair of the IEEE Indonesia section, I am happy to welcome you to Morse 2021. I would like also to thank everyone who has made this conference happen today. First of all, the Department of Mechatronics Engineering, the Faculty of Industrial Technology of Catholic University, who have been very kind to host this conference. Also to the IEEE Indonesia Control System Society, Robotics and Automation Society Joint Chapter, who serves as the technical co-sponsor for this conference. And of course, the speakers and moderators involved. While the scope of this conference might fall into the fields of control systems, robotics, and automation, but as a telecommunication engineering, I myself feel very proud to have this opportunity to speak here because the acronym of the conference is Morse, who was and still is one of the greatest inventors in the field of telecommunications. A conference is a medium in which researchers disseminate their research works orally and obtain direct feedback from the audience. Such a process will hopefully improve the research works, which will later contribute to the enrichment of scientific knowledge in the fields of electrical engineering, and at the end of the day, will benefit the humanity. This conference shall aim to enrich knowledge about the latest issues, opinions, bright ideas from researchers and academics. New innovations and in technology for a better future are emerging, including and especially in the fields of control systems, robotics, and automation. Collaboration between universities, industry, and government is important in creating jobs and developing civilization. I hope that Morse 2021 can encourage discussion and hope to inspire participants from a variety of teams to start collaboration within and across disciplines for the advancement of science. Sessions may also show important scientific progress and highlight the impact on science and technology. I hope all of you will have a productive and enjoyable time at this very special conference. Honorable guests, speakers, ladies and gentlemen, IEEE Indonesia, as a regional organizational unit of IEEE, serving the IEEE members in Indonesia, was founded in 1988, and in its development over the past 33 years, IEEE Indonesia has contributed significantly in various activities that encourage the role of science and technology for humanity in Indonesia. IEEE Indonesia, together with volunteers, members, and all stakeholders, have produced various activities by supporting of more than 20,000 IEEE conference publications and more than 260 IEEE journal publications by Indonesian authors since 1988. Despite these numbers, we still need to encourage the growth of scientific publications from Indonesian authors in high-quality IEEE journals. IEEE Indonesia has also sponsored and support more than 50 high-quality conferences each year. The results of the quality conference publications are published in the IEEE Explore digital library, indexed by Scopus, Web of Science, and other major databases, which have more than 5 million publications and more than 12 million downloads each month. As we all know, IEEE always maintains high-quality publications as part of the intellectual culture. IEEE Indonesia also holds more than 40 professional, technical, non-technical, and administrative activities each year for all its members. Currently, we have more than 2,600 members and more than 50 senior members consisting of professionals, industries, academia, and government. Currently, IEEE Indonesia also supports the development of 25 technical society chapters and joint chapters, which are each a forum for technical activities for members in Indonesia. IEEE Indonesia has also supported the development of 24 university student branches and 9 IEEE student branch chapters, which become a forum for technical and social activities that provide the best experience for Indonesian students and graduate student members. In addition, we also have a non-technical affinity group consisting of young professionals and women in engineering and one IEEE site on e-health and telemedicine interest group. This year, IEEE Indonesia has also initiated cooperation with the Directorate General of Higher Education of Indonesia in order to synchronize and support IEEE activities with the Indonesian Ministry of Education and Culture program, especially for the Free to Learn Free Campus program. IEEE Indonesia is also exploring cooperation with Indonesian industry in various activities. In addition, IEEE Indonesia is also actively involved in providing input in the preparation of related government regulations as well as other activities. Our most recent effort is to launch the IEEE Innovation Nation program in Indonesia with the hope that we could help support the development of new innovative startups by local people in Indonesia. I would like to encourage any of you who are not yet an IEEE member to join us and become a member to experience all of these opportunities, to work together and collaborate in these various activities. Finally, I realized that putting together a conference like Morse 2021 is not an easy task. We are grateful to all parties who work together to help build this very interesting conference program. We hope that Morse 2021 can be a fruitful and memorable event. Stay active, stay healthy. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Professor Hendran Toro. Ladies and gentlemen, we would like to request our last speaker to give his remarks and to officially open the Morse 2021 conference today. Please join me to welcome Dean of Industrial Technology Faculty of Parahyangan Catholic University, Dr. Teddy Yogasara.
Thank you. Good morning, good afternoon, good evening, whichever time it is where you are. The Honorable Head of Department of Mechatronics Engineering, Parahyangan Catholic University, the Honorable Keynote Speakers and Chair of the Organizing Committee, the Honorable Chair of IEEE Indonesia and Chair of CSS RAS Joint Chapter Indonesia, esteemed presenters, students, and all enthusiastic participants and guests. It is my pleasure to welcome you to the second International Conference on Mechatronics, Robotics, and System Engineering, or MORS 2021. And despite the COVID-19 pandemic that prevents us from meeting physically, we all are grateful for our health and for being able to participate in this important event. The Department of Mechatronics Engineering, Parahyangan Catholic University, or UNPAR, has put together an excellent international forum for academics, researchers, industrial practitioners, and students to embrace and share their latest research, techniques, and advanced development in the fields of mechatronics, robotics, and systems engineering. This event also serves as a useful bridge between academics and industries, and as a means of creating beneficial networks for the development of mechatronics and electrical engineering world. I feel exceptionally happy and grateful as this year Department of Mechatronics Engineering managed to bring this conference to the international level for the second time. And it is the first time for the conference to be held using online platform. Previously, in 2019, MORS took place successfully in Bali, Indonesia. This event in the future hopefully would be an iconic program of the Department of Mechatronics Engineering UNPAR. I feel very proud and pleased that our departments in the Faculty of Industrial Technology UNPAR have been consistently organizing and holding quality programs that promote acknowledgement and recognition to our faculty and university, both nationally and globally. Relating to that, ladies and gentlemen, please let me take this opportunity to introduce our faculty. Our Faculty of Industrial Technology was established in 1993 with two departments, Industrial Engineering and Chemical Engineering. Currently, these two departments have been accredited by the National Board for Accreditation with rank Excellent, which is the highest level possible, meaning that we provide the best quality in higher educational services. In addition, our chemical engineering program has also been accredited internationally by IAB, or Indonesian Accreditation Board for Engineering Education. In 2015, we proudly introduced the third undergraduate program in our faculty, which is Mechatronics Engineering. This youngest program has also been accredited, achieving very good rank. Currently, our faculty consists of around 1,500 students and more than 60 permanent teaching staff and researchers. Our faculty also offers master programs in industrial engineering and chemical engineering. Ladies and gentlemen, with regard to the vision of UNPAR, I hope that the development of the use of knowledge in mechatronics, robotics, and system engineering can also be focused on the utilization of Indonesia's natural resources and various local potentials, and subsequently bring them and introduce them to the international level. Moreover, I believe that this conference could be a means for facilitating and equipping us in facing the era of Industry 4.0, which is characterized by Internet of Things and cyber-physical systems. The advancement of mechatronics technology and knowledge needs to be directed towards intelligent production, cloud computing, big data, advanced robotics, artificial intelligence, and nanotechnology. With the advent of the fourth industrial revolution, many of humans' roles and jobs will be replaced by robots and artificial intelligence. Therefore, it is essential to prepare future human resources who have unique and superior skills, as well as spirits of transformation and innovation. Distinguished guests and participants, putting together morse 2021 is a team effort, and I first would like to thank the head of Department of Mechatronics Engineering UNPAR, the chair, and the organizing committee who have worked very hard for the success of this year's morse. Secondly, I would like to express my sincere gratitude to the keynote speakers, Professor J. Katupitia and Professor Meki Habib, who are willing to share their expertise and time for this conference. Special thanks also goes to IEEE Indonesia and CSS RISE Joint Chapter Indonesia for their significant support. Finally, I would like to once again thank all participants for taking part in morse 2021 and making this great event possible. I wish you all a successful conference with fruitful discussion and inspiring findings. The honorable participants and guests, by giving thanks to God, I declare that the 2021 International Conference on Mechatronics, Robotics, and System Engineering is officially open. Thank you.
As this conference has been officially opened, we would like to give our appreciation to the speakers and invited guests who have given their remarks at this opening ceremony. Before we proceed to the next sessions, let us take picture together. Please activate your camera, and one of the committee will guide us in this photo session.
Okay, ladies and gentlemen, we will take a picture together. We start with the first screen. We will have, I think, three screens. So, first for the first, sorry, we have 4 screens. We will take the first screen. I will count to 3. 1, 2, 3. Then the next, the second screen, I will count again. 1, 2, 3. The third screen. Okay, let's start to count. 1, 2, 3. And the final screen. 1, 2, 3. Okay, we done. Thank you very much.
Dear all conference participants, it is time for us to join the first keynote about autonomous agriculture vehicles and active implements for high precision operations. Our first plenary talk will be delivered by Professor J. Katupitia from University of New South Wales. Dr. Jonathan Chandra will become the moderator of the talk. Without further ado, Dr. Chandra, please guide us for the first keynote.
Good afternoon from the west of Indonesia, distinguished guests and participants. Welcome to the first keynote session of morse 2021 virtual conference. My name is Jonathan Chandra, and I will be serving as the moderator for the first keynote session brought by Professor J. Katupitia. Is Professor J here?
Yes, I'm here.
Okay. You'll be hearing a presentation from Professor J. Katupitia on this very timely subject. But before we get started, I'll read a short biography of Professor J. Katupitia. Professor J. Katupitia graduated from the University of Peradeniya, Sri Lanka, specializing in production engineering, and later completed a PhD in mechanical engineering, specializing in robotics. He later joined the University of New South Wales in Sydney, Australia, and currently a member of the academic staff of the School of Mechanical and Manufacturing Engineering. He was also the deputy head of the School of Mechanical and Manufacturing Engineering and did pioneering work to establish the mechatronic engineering program at the New South Wales University and was the head of mechatronic engineering program for more than 10 years. Now, he's currently managing director of Tronfield Robotics and Trontech Autonomous Systems, which is two sister companies developing an autonomous agricultural vehicles. Not to forget, his research expertise is in the areas of autonomous field vehicles and space robotics. Now, moving along to our session, please welcome Professor J. Katupitia, who will be speaking to us on autonomous agricultural vehicles and active implements for high precision operations. Not to forget, you may also ask any question related to the topics using the Zoom chat features. Okay, Professor, the stage is yours.
Thank you, Jonathan, for the introduction. Do you hear me clearly?
Yeah, crystal.
Can I share my screen?
Yes.
Okay, thank you. Do you see my screen?
Yeah.
Okay, right. First of all, I'm really very thankful to the organizing committee of morse conference and inviting me to do this presentation. So as I agreed, the title is Autonomous Agricultural Vehicles and Active Implements for High Precision Operation. Basically, my aim today is to tell you the kind of work we have done. This will be mostly on engineering side of work. We've done quite a lot of theoretical developments and they are all nicely written out there. And I will also show you where you can find the research work that we did in this area. But mostly I'd like to tell you the important aspects of autonomous agricultural vehicles, especially why we need high precision and why we need active implements. So basically what I'm saying by active implements is that implements themselves have some form of control systems operating while the implement is working out in the field. Normally in agricultural operations, when a tractor or some other prime mover is pulling an agricultural implement, the implement simply drags behind it without taking any active controls to do some improvements of its work. So that is what I mean by active implements. So you will see that the implements that I will be showing has some active components in them. Okay, so let me change the slides. First of all, my affiliation. So I am an associate professor at the School of Mechanical and Manufacturing Engineering, University of New South Wales, Sydney, Australia. I especially put this Sydney photo. Sometimes people get confused about New South Wales as a place in United Kingdom. I am right now actually in Australia. So this University of New South Wales is a place in Australia. It's one of the great universities in Sydney. We also have this website if you need to see what we do. This is mostly related to the Thorntech Autonomous Systems and Thornfield Robotics companies, but the work is actually shared. So my background, I have developed high precision autonomous agricultural machines over a period of more than 10 years. And the technology is actually commercialized, so it has got the United States patents as well as Australian patents. And we have also developed high precision autonomous bulldozers for Komatsu with some participation, collaboration with them. We have also developed high precision road construction machines to compact the ground by the sides of newly laid concrete slabs of highways. So these are all field vehicles, as you can see. So we are not working in the urban transportation or anything like that. Largely, the heavy vehicles operating in the field is my area of specialization. So autonomous agricultural machines, I'm going to describe this in a bit of detail, and that's why I have put all these steps here. So the example system that I'm going to present, which is, it does not have to be this system, it can be any system. So it is called a broadacre seeding system. By broadacre, what I mean is large fields growing crops such as wheat, barley, canola, sometimes grass for Japanese cattle market. So these kind of large areas growing crops are called broadacre farming. So in Australia, we have fields that are 10,000, 15,000 hectares large, and this is quite common in some parts of United States and Canada, and also it is becoming common in South America. There's not a great deal of land left in Europe, therefore the farm sizes may not be this big. I'm not 100% sure. So that is what broadacre farming means, and seeding is planting the seeds, and it does not have to be seeding. You can do plowing, you can do fertilizing, you can do weeding, all kinds of operations can be done, but in this example, I'm using seeding. So the basic premise behind the development of these machines is split the machine into two. One is a pilot vehicle, the other one is the implement. So the pilot vehicles are generally small in our design. In normal situations, the pilot vehicle or the vehicle in front is capable of pulling the entire implement regardless of what kind of work it does. Even when it engages the ground, the forces rise rapidly and the prime mover in front is capable of pulling this implement. But in our case, the pilot vehicles are very small, but they are supposed to pull implements that they cannot really pull. So how do we do that? So that is why this says that the implement has its own power unit. So this one here says implement has its own power unit. So implement is to some extent powered. So the implement driving power comes from the implement itself. And the pilot vehicle is fully instrumented. And we have these two vehicles controlled differently. You can see that the pilot vehicle is speed controlled and the implement is force controlled. That means when the speed is specified for the pilot vehicle, it is going to travel at a certain speed. You can imagine the scenario that if the implement's speed is different, then there's going to be a collision resulting in rise of very large forces at the point that joins the front vehicle to the back implement. But if you control this pilot vehicle as speed control device and the implement as force control device, then the implement controls these forces and adjusts its speed in such a manner that this force is maintained at acceptable level. That is why these two are differently controlled. And the implement has cost-effective sensors. It hasn't got any GPS or any complicated sensors. It is largely control systems only. The local sensing that is needed is there. However, the implement is very active, as you can see that wheels are driven, and at the same time the wheels are steered. Now, in addition to this, there are other controls that we have in our system, which I will show you in a minute. However, they are driven and steered for the time being. And the coupling is high tolerance fit, so there is no play between the implement and the vehicle, but also it has sufficient compliance. You can imagine when there is no compliance between a coupling, what happens is the coupling forces suddenly rise and suddenly come down, and the controller that is trying to drive the implement is not able to cope with these sudden high frequency force changes. So therefore we need to have sufficient compliance in the coupling, right? So if we look at the machine, so I have it shown here. Let's see if I can move this. So there are some chats. Let me go and see what's in them. Okay, so they don't seem to be needed for us now. I'll minimize that. Okay, so this is the basic description of the instrument. So what you see here as a John Deere tractor, that is this part here, sorry. John Deere tractor that you see here is the pilot vehicle. And what you have at the back is the implement. So if you go from left to right, you can, first of all, you can see there is a steering sensor that senses the steering position of the tractor. And there is a steering actuator, which is just a little motor mounted here that turns the steering wheel. In normal modern situations, you can directly interface to CAN bus and send some signals, but generally it is very difficult to break into the protocols. And then there are two GPS systems that is going to tell us the position and orientation of the machine. There is a Wi-Fi antenna, which doesn't do much. Then we have these wheel encoders, purely for research purposes. There is an inertial measurement unit that is needed for the autonomous guidance of these machines. There's a box containing all the electronics. And then there is also this tiny antenna that is going to give us the GPS correction so that GPS readings are very accurate. So the implement has its own power unit, as I mentioned earlier. And then the hitch point has a force sensor. I will show you details of this in a minute. And the motors are driven using hydraulic motors. I'll show you details of them in a minute. And these wheels are steerable. And also the implement steering sensor is somewhere here, which we will also see in a few other pictures in a minute, right? So that's how this is largely instrumented. You can now see that the implement has controls. So I need to explain parts, so let me check pictures one by one and show you what they are. So first of all, let's take a look at the actual implement itself. So we know the tractor part is quite familiar to us, but this is the implement. So we have the wheels that are driven by these motors. I'll show you the motors in a minute. And there is hydraulic supply coming from the power unit. And these are all controlled by the central control computer for the entire system. So this wheel is driven together with that wheel. The way it is actually currently connected is that they both get the same driving torque, because we are force controlling this implement. By force control, what I mean is that the hitch point should maintain a certain constant force. So you can imagine if one of these plows dig into the ground, then it is difficult for the pilot vehicle to pull. As a result, the hitch point force will increase. However, we don't want that situation. We want the hitch point force to maintain constant, at a constant, regardless of what the implement is doing. So who is compensating for this additional load that just came on board because the plows went down into the ground? Then these wheels will take up that force and maintain the connection force, a force at the coupling, exactly as desired. So the pilot vehicle is not going to feel any of these things. All these disturbances will be managed by the implement itself, right? So the seating implements can be lifted up and down. That is one control. And I will explain you this control that we have here. There is another cylinder and a sensor that is up here. I'll explain you that in a minute. So this is the power unit that I talked about, and in this implement, which is a small prototype, we just have 2 wheels, but if it is pretty wide, you can have any number of wheels in the longitudinal direction, and you can have many plows in here. But the pilot vehicle is not going to feel that this is a huge implement, because implement is powered by itself, and all that power is used for implements all controls. So I will show you the steering system of this. I should be able to change photos here. So this is the steering system. You can see this is one of the steering axis of the wheels. The other one is over here. And there is a steering cylinder, actuating cylinder, and also a sensor. There's a huge tie rod here. So let's take a better picture of this. You can see how the steering actuator is. This is the Ackermann steering geometry here. And there's a big link here that is moving this tie rod left and right, thereby steering it. And we can close the position control of the steering using this sensor and that actuator. So that's how we steer it. There's more pictures of it, steering actuator and the steering sensor. And that's the steering part of it. So now we can go to the driving part of it. So this is the wheel. And there is a hydraulic motor here, and this hydraulic motor is controlling the speed. So this is the hydraulic motor, and the speed sensor. As a speed sensor, you can use the GPS, or you can use encoders. Now, encoders are not needed in a commercial product. You can use GPS to sense the speed. But the speed, as I mentioned, is automatically controlled by the force control of the drive forces. It is actually not controlling the speed. It's actually controlling the drive forces to control the coupling force at a constant. So this is how the coupling looks like. This is much more modern than this. I don't have photos that I took recently. So there is a little sensor here, a high precision sensor that is measuring the misalignment or the angle between the longitudinal axis of the tractor and the longitudinal axis of the implement. So that is measured by this sensor, and I will tell you why that is necessary. And this is the force sensor I was talking about, which is preloaded, so it can measure the force going up as well as force going down. That means the force that is occurring in this axis can be sensed by this force sensor. So you can imagine this force sensor as the sensor that develops the driving signals for the wheels of the implement. It does not do anything to the tractor. If the tractor pulls, the force goes up and the wheels begin to drive. As a result, this force comes down and maintains at whatever the desired value. So that's what the force sensor is. And there are 3 controls, as you can see here in this particular implement. One is to drive the wheels. The other one is to steer the wheels. And then there is also another controller at the back, because I was talking about that what we need is extremely high precision. And we want to get to a stage where broadacre farming is like a factory. Everything is precise. Machines travel very accurately. Everybody knows where the crop is. So you can reduce the sensing. Next time when you come, you don't have to sense. You just go the same way that you did plant them, and you will find the growing crop. So this third sensor is doing something special, and I mentioned that I will explain you about this cylinder and that actuator at the far end of the implement. And what it does is, if for some reason the implements, this trailer part shifted, let's say it shifted towards our left because the ground could not hold it, and then the misalignment sensor will sense that it shifted off the path. But that is okay. It can shift a little bit towards our left. However, we need to have these points, the implement's actual ground engagement points, very accurate. So this entire carriage can be shifted left and right by this actuator. So our software detects that, the trailer or the implement went off the path by maybe 1 or 2 centimeters, and that angle will be sensed by the angle sensor, and control action will be taken by actuating this cylinder to adjust this implement so that the tools actually travel extremely precisely. So that's our requirement, that the tools really should travel really, really precisely. So that's the description of my, the hardware description, so I explain parts. And we can take a look at how this machine runs. So I'll play this video, I hope it will play. Volume off. So you can see that in order to demonstrate to you how accurately this machine runs, we have pulled a string. You will see this white wire, white string, 60 meters long, very taut, high tension, and we don't use it to control the tractor, but we use it to show you how accurately it runs. So if I play this video a little bit longer and stop maybe somewhere here, I will show, now you can see the string line. So this is the string line, purely used for demonstration of accuracy, not used for control. And we have a camera here. This camera is looking down towards the ground, and there is this aluminum angle in which we have placed a meter ruler. So the camera sees the meter ruler against this string line on the ground. And that way we can clearly show how accurately this machine runs when it runs. So let's watch this for a moment. This is a very long video, so I'm going to jump from time to time. You can see the force sense and all of that is here. So the wheels are being driven. You can see that it is very steady. It is not erratic, extremely accurate. And all of this is through the control systems that we developed. Most of these control systems are quite robust, because you can see that it is engaged in the ground. Basically, there is no driver. Wheels are powered by the blue power unit of the implement. The pilot vehicle is only providing the guidance and all the control signals that are necessary for the implement. So you can, if you pay attention to the back wheels, you will see that back wheels actually steer at the far end. So when it goes to the far end, we will fast forward it. So it's traveled about 300 meters. And all the parts are planned. I will also show you how we plan parts for these machines. So our customers can actually generate those parts for their machines. So somewhere here, if you pay attention to the implement's wheels, obviously we know that the tractor's wheels are going to steer, but if you pay attention to the implement's wheels, you will see that implement's wheels also will steer. As a result of the turn that is coming in. So you can see that now they are steered towards the inside. So maybe in a minute they will steer more. Yes, now they have steered quite a bit in there. So it's lifted the plows, and whenever we lift the plows, we take force control off. Force control is quite unstable when there is a large angle between the two axes of the tractor and the implement. And as soon as it aligns again into the right field position, then you can put the plows down and continue this operation again. So let me see if I can move a little bit ahead and save some time. So this is, in a minute, it is going to show us the camera view that I described earlier, explaining the tractor's accuracy. So this is a tractor's, the rear axle of the tractor, how accurately it is following the path. You can see that, if I can stop this somewhere. So all of these darker marks that you see here, they are 1 inch apart. And all of these darker marks up at the top are 1 centimeter long. So this is the line that I described you, which is on the ground. Camera is looking past this meter ruler down to the ground. You can see that this doesn't deviate more than 1-2 centimeters at most. So most of the time it is within 1 centimeter as it travels. So this is traveling in rough ground, and it is engaging with the ground, pulling these plows, and you can see that most of the time it is staying okay. So I'm going to move this to further down to see how accurately the implement is going to travel. So this is the implement's accuracy, somewhere here, maybe earlier. So you can see that this is going to track by the seeding points of the seeder. So how accurately those points that are actually doing the work is going to work. So it is supposed to be at 300. So if I stop it here, if I can. So this is somewhere 300, this is 250, that is 350. So it's 50 millimeters here and there. It's supposed to stay on 300 mark, and most of the time, I'm sorry that it is not 100% clear, but it's 300 is here. You can see that the implement is traveling quite accurately using these control systems that we've developed. So that's basically, oops, somewhere here maybe, that's basically how the system works and keeps on shifting from pitch to pitch as it travels. So once it's plowed one set of lines, then it moves towards the right, and that way it keeps on looping and keep on going. So that's what that system is. So this is, as far as I can explain, how an active implement is operating out in the ground, out in the field. Okay, so let's move on. So we also have made other things. So these machines are not as complicated. We did this for one of our Chinese clients. These machines are not as complicated as you can see. It is not dragging anything. This is a 19-meter wide. So let me see if I can move this away from here. Yeah, I can take it away. So this is a 19-meter wide sprayer, boom sprayer. They are all folded now. But you can see this also, obviously, this is very smooth surface. However, you can still see that they are traveling very accurately. So what I want to do is that this kind of technology is not so this machine is very good. These time after the exact time around. So highly precise. So this is another machine that this is, as you can see, this is a tracked vehicle, a very small tracked vehicle, which is also for a Chinese client. These machines are really not conducive to be made to modern, state-of-the-art advanced machines. However, you can still develop very good control systems to deal with these machines. So unlike the other machines that I showed you a minute ago, this machine is taking square turns. So smaller tracked vehicles, obviously driverless again, they can take square turns. When they go to the far end, the other John Deere tractor took a circular turn, and these ones normally take square turns. And they are all programmed so that the system figures out when it goes to the right point, that it turns, lifts the plows up like the other one did, and takes a turn and aligns again itself and keeps going. So we just wait for this to take the turn and go around. So when you look at it, you will see that it is turning too much, but that is not what it is doing. It is actually turning 90 degrees to the path that it came. Obviously, the camera also moved. But when I show you the path generation software, I'll show you what it was doing. So now you will see that it turns almost 90 degrees so that it is parallel to the path that it came earlier. So, and then it speeds up. As soon as the turn is complete, it speeds up, puts the plows down, and keep going. So tracked vehicles as well as the wheeled vehicles, they both work equally well. So I'm going to skip this and keep going. So this is another, so a company that had an association with UNSW used our software earlier. You can see how fast these machines can work because they are so robust. As it comes to the turn, it slows down, takes a turn, and you can see the speed at which it is traveling. So this was filmed by chasing it after using a pickup truck. So it speeds up as soon as it hits the straight line. Obviously, it's a demonstration. The sprayer booms are folded at the moment. Okay. So as you can see that this is now becoming widespread, and it will be quite commonplace like the cars that we see out there. So one of the important aspects for all these people is the generation of parts for their fields. So normally they specify these coordinates. This is a simpler version of our path generation software. So what we do is whenever your client comes in, we give them this software. And this software they can use. Obviously, right now they are using a configuration file plus the coordinates. But in the future, they can enter all of these things in here. Then they, based on their machines and based on their turn types, then it will generate a path here. So let's see if we can run this path gen algorithms. So this is what you normally do when you start. There is no path, or system doesn't know where in the world this is. So when you say submit, what you basically do is you are sending these coordinates to a server that we provide to our customers, and then it will ask you to wait, and it will generate the path. So then you can get the path, and obviously you can save it somewhere. And so I'll overwrite that, and then it shows you where the path is. So to see some difference, maybe we can change one of these coordinates to some other number and submit. And also we provide them 3 different types of paths. So now it has, the server has generated the path and sent it back to us so we can get it. And so that's different because I changed the coordinate. And you can see that the turns are all circular turns because we were asking U-turns, but you can also ask for square turns. And if you submit, then it will give us a path that is generated for example, the tracked vehicle that we saw, it was taking 90-degree turns at the end of the path. And then we should see them all 90 degrees. Sorry. So these are all 90 degrees. So this is why you saw that the tractor was turning more than necessary kind of things that we saw was one line was boundary, but they are not going to be. So normally we get another run that is along the boundary to cover the whole land. Okay, so that shows how the path generation software works. And it also tells you the network quality. Sometimes out in the field, some of the clients cannot use this. So then they have to, this will be read, and they have to go to their office and generate the path. And corner coordinates, if there is anything wrong with this corner coordinates, then it will also complain about the corner coordinates, and the path is ready. This will go green, then you can get the path. Okay, so that's the path generation software. And these are all available for customers to use, and they're very important. And also monitoring is very important. Well, we are not promoting monitoring that much, but once the machine gets going, so we've developed these situations where the clients can log in to their machines by logging into our server, and their machines are sending the data to the server, and they can watch the behavior of the machine by logging into our server. And here it says what is this current speed of the machine, how much fuel is there, how much water is there, how much chemicals are there. This will show how many satellites are actively connected and so forth. So this is for them to monitor what's happening with the machine. We also did some research on bulldozers. Bulldozers are very robust machines, much easier to control than tractors because their ground holding is really, really good. Precision is still important in bulldozers. So in mining, for instance, you have these lines of bulldozers, and why they have these gaps between them is because they are not precise, driven by drivers, and they can collide, leaving all these windrows. However, if you can actually run them very precisely next to each other, and then you can actually avoid having to do this job over and over again because of the windrows. So these kind of vehicles are also used in agriculture, which is one of the very popular agricultural tractor that is used by large farms, which is a Challenger of the Caterpillar company. And you connect all these implements to this. These large vehicles don't take square turns, they take circular turns. However, they are very good machines. So we can discuss a bit of why we do all these things. Now, if you look at the automated machinery and autonomous machinery, the automated machinery, they are able to react to sensing, but the unexpected circumstances are very well known. There is no surprises in them. And all decisions are built in, largely coded, without having to go through any intelligent software. Whereas autonomous machines are slightly different. There is a wider variety of sensing is needed because the unexpected circumstances are not entirely known. So adequate software technologies must be there for decision making. Now, why autonomous? One of the reasons is to replace human. Everyone thinks that, we can get rid of human, and that is the main aim, and that is where the money is, which is quite incorrect. It obviously reduces the labor costs, but in a country where labor costs are very low, then someone is going to ask you, why get rid of the labor? Because it doesn't cost us anything. So that is not a driving factor. And elimination of human error, because if humans cause elimination of human error from the safety point of view, you cause collisions and you run the engines in an inappropriate way, therefore their durability comes down, and all these things. Yes, there are some useful points, but the real points are the exceeding reasons that go beyond human capability. For instance, the precision unachievable by human operators, the precision that I showed you against the taut string as the machine traveled along. Who can drive like that? No one can drive like that for 10 kilometers. It has to be autonomous. Endurance, who can sit in this machine day in, day out, traveling 10 kilometers that way, 10 kilometers this way, 10 kilometers that way, 10 kilometers this way, continuously, is very tiring. And what you need to do is to save the operator, you have to stop the machine, and that machine is capital. So you are tying down the capital to care for the human operator, which is a very good thing to do. But if you can get the maximum benefit out of the machine by running it around the clock, you should be able to do that, and a human cannot do that. Repeatability. How can a human sense it and repeat exactly the same thing? It can't do that. And the situational awareness, there is only a limited amount of knowledge or data that our heads can handle, our brains can deal with, whereas these computers can deal with large amounts of data, and they can do incredible things that we don't do just because we are unable to do, or we didn't think about that we could do these things. So there's a lot of data as well. So I'm just checking time, okay. So 10 more minutes about. So precision in autonomous agriculture machines. Why precision is needed, especially in agriculture? So crop can be planted according to specified layout. Knowing crop location drastically reduces sensing. So if you have to go into an agricultural field, from the get-go, you have to start sensing to find out where this crop is, and that is very expensive. Sensing is actually one of the most expensive things that we do. Knowing crop locations drastically reduce wastage in substance application. That means if you're applying fertilizer, if you don't know where the crop is, you have to fertilize the entire field. Whereas if you know exactly where the crop is, then you can direct your fertilizer to the crop. As a result, the fertilizer usage can be cut down by about 2/3, nearly 2/3. And someone who's spending $1 million on chemicals or fertilizer, if it is cut down by 2/3, you're already saving $660,000 in one season. And that is about, with that money in one season, you can cover the cost of this machinery. Maintaining structure further facilitates automation. That means if you plant these things very, very accurately, then you already eliminated sensing. Next time you follow exactly the same path, applying fertilizer to exactly where the crop is. So if something is very structured, then automation is easier. If you use automation, it becomes structured. Structure helps automation, and so forth. It becomes almost like factory-like after some time. And also the crop damage can be avoided during subsequent operations because you exactly know where you planted the crop. It's always planted according to pattern, and you can now blindly drive without worrying about where the crop is because you planted it very accurately to start off, right? So precision autonomous agricultural machines, why is it so hard for us to do this? What makes a machine precise? That is being able to do the same thing over and over again. So we had to obviously use high accuracy, low noise sensors, data fusion, and localization, and all of those things we know, but we can't position this machine on the path all the time. Why? So here's an example. You take the train on the tracks, there will always be more than enough lateral forces because the train wheels are guided by the tracks. So always, the train is never going to slip sideways. Why? Because the tracks are providing sufficient forces. The train does not steer itself. Agricultural vehicles steer them, but train does not steer itself. It goes through a curve quite nicely. Exactly, precisely, because the tracks steer the train. And these lateral forces, the exact dosage of lateral forces required to steer the train is delivered by the tracks. So train always go exactly on the same path. And if you're trying to get the tractor to do this, it is not going to work like that. Why? There will often be not enough lateral forces to hold the tractor on the path as it traverses. Soft soil gives way and tractor shifts sideways. Tractors steer themselves, demanding the ground to provide the lateral forces, and the ground fails to deliver sufficient lateral forces, not like the rail tracks. So the mismatch between the lateral forces provided by the ground and the required by the steering causes the vehicles to deviate off course. So therefore, we go and design control systems or find other solutions, and all these machines, in comparison to the wheeled vehicles, these machines have very long contact patches and their ground holding is really rock solid and they don't get shifted that well. Same with these delta tracks, this kind of tracks, these are steerable and you can use those tracks and you can also drive them. So it is not only that you can bring it back through not slipping, but also the drive forces can be vectored back to the track. And these are very good methods to avoid sideways shift that destroys the crop layout in soft soil. And these four-wheel steer, four-wheel drive systems are also very good, that you can have modular steering. So this module is completely independent of this module and so forth is also a very good solution to keep the machines on track. So we have a machine like this in our lab, which is going to be entirely force control. You can see 4 force sensors, one there, one here, one there, and one there. So at any time, we don't have to estimate anything, predict anything. We know the real forces that this machine is undergoing. And if you know the forces, you know how to control it on the track, along the path. And you can adjust these forces through control systems. So we have done these nonlinear robust control methodologies, the sliding mode controllers with force observers and slip observers, as well as model predictive controllers and various other methods that we have used. So we have published them in this book. This is my PhD student, Javad Tagia, who finished his PhD about 3 years ago. So this has applied guidance methodologies for off-road vehicles, which are the algorithms that we developed over many years. So we published this about a year or maybe 2 ago. Right, so as far as safety is concerned, consider what we provide as autonomous vehicle designers. We provide steering, propulsion, and implement control. But what really causes injury or damage is propulsion, how you drive this. So you need to make all these safety provisions. And there are 2 levels of execution. These are the SAE 6 levels. And they are divided into 2. You have these 2 levels of execution, that is steering and propulsion. It is driven by a human and steered by a human, or driven by a system, which means a computer steered by a system. And 2 levels of monitoring. Who is looking after the machine? Is it a human or is it the system itself? And 2 levels of fallback. When the automatic system breaks down, is it a human who is going to take control, or is it the system who is going to take control? So level 6 will be system is doing the execution, steering and propulsion, system is doing the monitoring, and the system is taking it over. It is very difficult to do this in an urban setup, but in the field scenarios, this can largely, this realization is quite close. We can actually achieve this. Because all these dangers due to motion is quite subdued and reduced. Therefore, we can actually do that. There are no urban canyons, good GPS reception is there, mostly flat land, there are no humans, a widely open field, and all of these things added together gives us very close to level 4, 5, 6. Well, we're not there yet, but at least level 4, level 5 is quite easy. So finally, to finish, so we have another 5 minutes or so to go. So of all people who try to use autonomous vehicles, we are better because, especially those who develop autonomous agricultural machines, We mostly operate in private land, so we are largely immune to litigation, various legal action, protests by people, and so forth. Is largely not against us yet, or may not be ever in the future. The land is mostly sparse. You don't have to consider collision avoidance constantly, but you must have collision avoidance systems put in place in these machines, but they play a minor role. The agricultural terrain does not allow hazardous driving, such as in mining. In mining, it is very dangerous. So you need to have very well controlled exhaust control, sparks and things like that are very dangerous. So mining is much harder operation than agriculture. And we do not have to confront hostile unknown scenarios. We are not fighting wars. This is very peaceful scenarios. That's another positive. So our operations will always be to make people live. So it is quite rewarding than to kill. So therefore, agricultural automation has a very good future. It's quite possible to achieve. And I'm pretty sure that very soon, there are already agricultural machines slowly operating in the fields. This will be quite widespread as time goes on. So that's the end of my presentation. If you give me 1 minute to look at the messages to see if there is anything that I need to answer. Okay, there are no questions here. I don't think, okay. So there's one, let me see if there are how many questions. That's not. Okay, I got one question. As the implement is attached to the main vehicle, how do you control the path of this implement to accurately follow the path of the main vehicle, especially when it is maneuvering? It is very important. Yes, it is very important. We are now currently working on similar case. That is Tugger train system, which is quite similar to your system. Thank you very much. Okay, I will see if there are similar questions. That's no question, not for me. Okay, yes, this is quite important. So what we actually do in our system is that we have two controllers because we have more degrees of freedom that we can control. Like we can steer and reposition the back vehicle as well as the front vehicle. So they're both steerable. And we implement almost the same controller for the tractor's important point that is following the path, as well as this implement's important point that is following the path. So of course there is a constraint at the hitch point. However, largely because we can steer the implement, we can maintain the implement's point of interest on the path. Provided that we don't have extremely sharp acute corners and so forth. So we actually implement two identical controllers. The details of this you can see in the book if you look at how that is done.
Thank you, Professor. Thank you very much.
Please go ahead.
Thank you for thank you very much, Professor J. Katupitia, for addressing this interesting topic on, we could say, high precision farming. I hope everyone here gets every detail from the presentation. I may have some questions. In the presentation, you state that the commercial usage of the vehicle doesn't need any encoders for the positioning. Is it true?
Encoders are actually not used in the commercial products. We did not use encoders, but I mentioned you about slip observability in some of our control systems. So at that time, we wanted to see how much slip is taking place. For that kind of measurements, we use the encoders for both. So you can actually take the GPS generated path and the encoder generated path, and the differences between these two tells us how much slip is going to be there. You can actually estimate the lateral slip by measuring the encoders, because you can plot the encoder generated path and the GPS generated path, and the lateral shift is going to give us the actual slip. You can do that in real time.
see. Thank you for the answer. And one more question. There's a question from Unpar, maybe here. Wait a minute. What is the maximum range of the autonomous pilot tractor?
Maximum range?
Yeah, maximum range.
The distance that it can travel?
Yeah.
It's as long as there is diesel, it will travel. So not this small green tractor, but the orange tractor that I showed you, we ran it for 8 hours non-stop.
Oh, that's long enough.
Yeah.
Okay, is there any question from the participants? Okay, we have a hand raised from Muhammad Abu Malik.
Thank you, Professor Jay. Just have a quick question. Like, I understand you use the GPS for locating the vehicle. So if my application is in narrow space, you know, GPS error sometimes can be around meters. So can you please elaborate if I decide to go with sensors or like IMU in terms of, getting position, maybe velocity. Just if you can elaborate on using IMU instead of GPS based on your experience.
So the problem with the IMUs is that the quantities that the IMU is sensing is acceleration and gyro rates. So gyro rates are very useful if we are on a drone or something like that, but on a ground vehicle, gyro rates are not that useful. So it is the accelerations that we measure. And if we need to eventually localize it, we need to know the XY coordinates of this thing. However, most of the accelerometers have these biases. And if you have a bias in the sensed quantity, acceleration has a bias. So when you integrate this to get the velocity, the bias gets integrated and the velocity gets shifted. And then when you integrate it once more, then you get the position. Bias is twice integrated and your position reading is quite wrong. So only thing we can do is if every now and then we can hook on to a landmark that we know of or we have seen before, then using the landmark details as the position fix, when the landmark is gone past for about 7 seconds, we can keep going with the IMU. But after some time, IMU reading has deteriorated again. And so one of the best things that we can do it's like in a wide open space, this is certainly not a problem because there is good GPS. And on the other hand, there's nothing to sense because you will not see anything. But in the situation that you are describing, then there are a lot of things around you, but GPS is not one of them because GPS is partially covered and it's not giving you very good readings and so forth. So scan matching is one of the very good methods that you can use. That means you take a scan of what you see and move a little bit because you are constantly taking these scans at a very high frequency. Then you get a new scan and then you can match what was the old scan. You will only see part of the old scan in the new scan, but you need to identify that part that you saw in the last time instant and that you saw now. And then you can shift and match these two parts that are common, and that shift generally, the rotation and translation that you need to do to get the old scan to match the new scan or the new scan to match the old scan is generally a very good indication of how you moved. So scan matching is one good way of doing it, or you must have landmarks. Landmarks also can be illuminated strips, for instance, that you saw last time and you're seeing again in this one. So how positioned it is in your scan, and that way you know by how much you turned and by how much you moved. So that is the only the fusion of GPS and IMU is only useful when GPS for short periods of time when GPS disappears. IMU GPS fusion will be good enough for you to survive until GPS comes back again. The data fusion with GPS and IMU is really not a good solution when you don't have very good GPS.
Okay, thank you for the answer, Professor Jay. Is there any more questions? from the participants? We do still have 10 more minutes. Okay, I think this will be the end of it. Okay, once again, thank you, Professor J. Katupitia, for sharing the information. We'll be going to the next, the secondary session.
Okay, thank you so much for inviting
Thank
me.
you, Professor J.
Thank you.
And
Take
my
care.
Rika from Bandung.
Okay, thank you very much. Bye for now.
Indonesia traditional culture is very rich. We have so many cultural performances. As Bandung resides in the land of Sunda, we would like you to enjoy one of our traditional dance performance. It is Jaipongan dance, which exhibit enchanting movement of the dancer. The next Jaipongan dance performance is named Bentang Bandung, which show the beauty of Sundanese women. Ladies and gentlemen, please enjoy Bentang Bandung.
Bintang Bandung, bintang Bandung, bintang bintang tinggal di langit Bandung, bintang Bandung, bintang Bandung, matak nari ambil bintang Bandung.
Welcome to Parahyangan Catholic University, where knowledge and experience are sought and great ideas are highly valued. This is the place where traditions are nurtured and history is made. Located in the mountains of North Bandung, UNPAR strives for advancement and innovation in 16 fields of study, namely economics, management, accounting, law, public administration, business administration, international relations, civil engineering, architecture, philosophy, industrial engineering, chemical engineering, electrical engineering in mechatronics, mathematics, physics, informatics. UNPAR provides an accommodative learning environment that creates outstanding graduates who are responsive to current opportunities and challenges. This is the campus where all dreams are inspired and passions are pursued. Through a continuous desire for excellence, achievements after achievements are made possible. UNPAR is a place where diversity is respected and community is built. Divinity, truth, and integrity have become the foundations of our academic culture. With various extracurricular and campus activities, UNPAR has been able to provide a comprehensive education while building the essential virtues of thriving in the present and preparing for the future. With decades of experience and solid foundations, from generation to generation, UNPAR has been recognized at national, regional, and international levels. We proudly acknowledge our professors for their expertise and our staff for their dedication to service. We heartily embrace the trends in digital transformations by adapting to current and future needs and challenges in the context of education. UNPAR believes in developing local potential on the international level. Thus, internationalization is an essential part of our commitment to provide our students and staffs with the needed exposure. This commitment is supported by high-quality facilities and infrastructure throughout the campus. Our efforts towards the future are guided by the spirit of Bakuni Yangri Gunu Sunchaya Bhakti, understood as based on the belief in God, the advancement of knowledge and devotion to the community. Compassion and humanity have become the center of our academic endeavors, which are ultimately dedicated to society. Welcome to Parahyangan Catholic University, the answer to the future. We begin here and now.
Dear all conference participants, our second keynote will be delivered by Professor Maki Habib from American University in Cairo. The topic is Bioinspiration, Intelligence, and Autonomy. Dr. Bagus Artayo will be the moderator of the talk. Without further ado, Dr. Artayo, please guide us for the second keynote.
Good afternoon, ladies and gentlemen. Distinguished guests, Professor Maki Habib, welcome to virtual Bandung, I would say. And all participants, I would like to give you warm regard from Bandung. Right now, we will follow the second speech from Professor Habib. Firstly, I would like to read the biography of Professor Habib. So Professor Habib obtained his Doctor of Engineering Science in Intelligent and Autonomous Robotics from University of Tsukuba in 1990 in Japan. He was selected research scientist at Riken, Japan, and senior researchers at Reiso Laboratories, Japan, and also visiting research at EPFL, Switzerland. He was a visiting professor at the Asian Development Bank, associate professor at UTM Malaysia, and a senior manager of MCRIA for engineering, project, and industrial consultation Malaysia. He was a leading senior research scientist with GMD Japan leading telecommunication research group. Associate professor with Monash University, Australia and Malaysia. He developed and led the mechatronics engineering program. He was appointed as a full professor of robotics and mechatronics at Swindon University, Australia, Malaysia. And he was an invited professor at KAIST, South Korea, residing professor at Saga University, Japan, and since September 2007, he is a full professor of robotics and mechatronics at AUC, American University in Cairo. And Professor Habib was also a visiting professor at many universities around the world, such as Nagasaki University, Japan, Hokkaido University, Örebro in Sweden, Norwegian University, and other university related to Toyota and ABB. Professor Habib also served as editor-in-chief of the International Journal of Artificial Intelligence and Machine Learning Regional Editor, and associate editor of 10 international journals, an editor board member of another 10 international journals, besides his leadership as a member of international organizing a program committee of more than 20 international conferences every year. Professor Habib edited more than 14 books, published more than 26 chapters, and also more than 275 papers at international journals and international conferences. I think now we are all curiously to hear the speech of Professor Maki Habib. Please, Professor, the stage is yours.
Thank you very much for the introduction. It's my pleasure actually to be here and joining the conference, the MOSI conference. And good afternoon to all of the audience. And I hope that through my presentation you will enjoy it and having some of the information that will help to guide your research. So I will try to share my presentation. So the title of my presentation is Bioinspiration, Intelligence, and Autonomy. And here we are reflecting all of the three keywords for the bioinspiration, intelligence, and autonomy in association with the field of robotics. So you know that the evolution of robots or the field of robotics in the recent modern era started in by the end of 50s and early of the 60s, and the main development was focusing on industrial robots, and then the dimension of the research in the field of robotics start to expand to cover ground mobile robots in all aspects of it, sea mobile robots in all aspects of it, aerial robots, drone in different types of structure, from micro to larger scale military one, humanoid robots, biomedical robots. We have a service robot, and normally service robot is growing to go to the different dimensions actually, that you have a robot that can replace a human being, you have robots that can work on human being, and you have robots that can work together with a human being. This is actually evolving toward the development of a personal robot, especially in the developed countries where the aging population is growing, and they need to have support and help. But the lack of people actually to give such as services is not actually facilitating such help. This actually opened the way to develop robots that can, with the shape of robot, with affections, that can work together with human being at home. Also, the development expanding to the space and expanding also to the here is the first key word that in my talk I'll talk about the bioinspiration, because there is a limit of the conventional way in the design, and the bioinspiration will open a new actually spectrum to look to the nature as a model and develop new design and structures supporting by eco technology actually that will work in harmony with the environment while supporting humanity. So these are quick examples actually about the industry. You have industrial robot for welding. Mainly actually you have industrial robot widely used in the automotive industry. Heavy number as you see it in the production lines. You may see it in the painting very widely. If you see now the large companies in automotive may produce more than 12 million cars per year for a single company, and that's by having human alone would be very difficult to reach such a number, but by automating that process, using a robot will be essential in terms of quality and in terms of speed and in terms of cost. These are examples of painting, different types from external and internal painting. This is cooperating. You have two robots that can, or multiple robots that can work together to cooperate doing a joint task. Here is the sophistication will come when you are developing fingers with a force sensor that can interact and detect the object and take care of a soft object while interacting with it. Also, there are some breakthroughs actually started by 90s, end of 90s, and now up to now actually is continuing, is to develop a mechanism, especially starting with Honda when they developed the humanoid robot, to have a humanoid robot that can freely move without having it being chained to a structure and being afraid from falling down. So Boston Dynamic later on is making a big breakthrough actually in terms of design structure and mechanisms. This is one of the example actually is a bio-inspired by animal of 4 legs. Having this is the base of the robot, and you can integrate to the robot different things. You can integrate a robotic arm, you can integrate for surveillance, a camera and sensor, you can have a gun for security if you are conducting a surveillance in a high value zone. So this actually it's and the key issue actually of these in the design is the recovery. Recovery means when it is falling down, it will not harm itself while it's going to recover and stand again and conduct the task properly. This is the already evolved design of the first Honda robot, but this is the latest one. It is telling us it's not just moving freely, but also it can interact with human beings through natural language. Can through a camera here, stereo camera at the face, can recognize faces and associate or talk to them or cooperate with them for a specific task. These are the robots of Boston Dynamics, in which actually the humanoid actually can work on 4 legs and can work on 2 legs. It's easy to recover. Jumping and running for a humanoid robot is quite a critical issue. And Boston Dynamics, this is actually a main breakthrough in the development of a humanoid robot, where the robot can run and cross obstacles without actually being slowing down. And also, if it's failing, it will has the ability actually to recover. Sure, when you say have the ability to recover, I mean there is something inside the robot can recognize this situation and recover from it. So it means there is sensing capabilities, information, perception, cognition, and reasoning about the situation. And this should be done in a very fast time. That's where the computational issue and the evolution in the computation is critical actually to deal with such a big amount of information in order to reach a decision with a very, very small amount of time that will enable a robot actually to conduct its job while avoiding obstacle and harms. Also, in the future, or not very far future, you may have a humanoid robot working either alone in certain factories, especially for the factories that are critical in terms of safety for a human being, or it can work together with a human being within the same shared space. You may also see, not far from now, I mean within the 10 years, possibly, or a bit more, robots within small shops along the road to deliver services like a beverage or food or sandwich or etc. Also, there is a you know after the 2000, all of the evolution and the development in the robotics area started from science fiction, and then from the science fiction, researchers start to, while the technology is evolving, try to develop and try to adapt the science fiction idea and put it in reality. So this is a movie actually called Surrogate, where being introduced as a robot representing human being with all capability of sensing, but all of this information will be sent back to a station, and the actual person is interacting with this person, and which I mean, this is the robot side, and authorize the robot to act on his behalf or her behalf according to the need. And the robot, once it's done the work, will return back to a station to charge itself. This is how the movie actually show the situation. And after the movie, normally people start to have it as a humanoid moving outside, and there's information coming, collected to the station, and the person actually is interacting. Sure, at the beginning will be limited capabilities and limited functions, but gradually, as in any research, you are building the platforms, establishing the essential functionality, and then, as in all research actually, it's like accumulated the process that you are building up gradually to reach better and better according to the level of development. Here, they started also during the last 10 years or a bit more, is to develop, which is mimicking the surrogate actually, to develop robots mimicking human being, and especially when we are talking about personal robot, a robot that's going to work with a human being at home, or interacting through human aspects of affection. So they develop, especially if you see in Japan, this was in Japan, developed a robotic character mimicking human being. And that is a base for future to have a personal robot living with a human being at home. If you are thinking about the developed countries, the rate of people living alone is increasing in a rapid way. And there is a need, because now helpers, young helpers actually, are refusing to extend or participate or be employed in a job for supporting a service for elderly people. And that's a critical need actually, to have people or robots actually to do the job. Since the people are not available, then the other alternative is to develop robotics for this purpose. And the space actually, instead of having a human flying in the space, so you have a robot actually mimicking human that can fly and move around to conduct a certain maintenance or monitoring or specific required action within a specific mission. And this is the well-known guy who started this area of developing a robot that's mimicking human being. And this is the robot side, and this is the actual person. He's a professor at Osaka University in Japan. Also in Stanford, they develop a humanoid robot, the submarine type, that can communicate and interact and act under the sea. There are different types of submarine actually with different capabilities. A submarine that can be being integrated with human being and go, or submarine that can have no human being but with limited capability in decision making that's still required to have a human to be in the loop. And you may have a submarine that's completely autonomous, integrated with different types of sensors that can go for a specific mission within the sea environment. Also, the development being extended beyond the submarine and the ground to the flying robot. And the flying robot, Festo actually developed a bird with the flapping wings. And also you have a micro level of flying robot being developed. And actually, I am personally engaged. I have a master's student is developing a flapping drone that can normally the size of can be different from a very micro level to a large scale flapping. And Festo demonstrated this one in a very successful way. If anyone can check the YouTube and can see the demonstration of this bird perfectly. Also, the development of quadcopters as drone now is increasing from micro level to a large military level, and in between you may have a lot of different capabilities. And not just using a single drone or single quadcopter, but also the integration between different quadcopters. In my lab, actually, we are developing different structure from micro level to a large level quadcopters for different possible mission. Mainly now we are focusing on the control and the navigation to generate the required trajectory and cooperating between multiple drones. Also in the military, it has the big actually consideration of adopting robots within the military, from the fighters, planes as aircrafts, to the ground tanks, missile launchers, and also to adopting actually a humanoid soldier. So you have it actually, and all being coordinated, because the capability of communication and integration to cover a large area is essential, and they are developing a lot of things in this domain. You know, robots can cooperate among themselves and can cooperate with a human being for different purposes. So this robot has a dual arms. It can do the cooperation between the arms to conduct the job, while here you have a multiple robots can work together to coordinate the job and complete it successfully. Also, robots, as I mentioned earlier, for the personal robot, it's coming in different shape, in the recognition through the camera, in the natural language interaction, and the supporting for elderly people at home, and the entertainment, etc. this is another example for a medical type support, which is exoskeleton. Now it is widely used in many hospitals around the world to support people that have problem with their motion capability. And here is the delivering of food for different purposes, whether inside a hotel or at the hospitals, etc. And you may see in the future a doctor robot that can go and diagnose and collect information. Here is the surgery. This is very widely used nowadays, actually, and it's been proved successful in terms of accuracy and time recovery for after the surgery, because they are limiting the details of the surgery on the body of human being. And that's why the recovery time would be fast. This is the nanorobots. Actually, I have a PhD student working in developing the structure and that's going to control a nanorobot, and he is almost at the end of concluding the three-dimensional control of a nanorobot to move the intention, but not because we are mimicking the operation to move in the vessels, mimicking human blood vessels and the operation. In the future, that's already started in the movies. You may see a lot of movies actually where the robot or being integrated with the robot human organs. And one of the key organs actually that's been integrated with the robot is the human brain. That's appearing where in the science fiction movies. So in the future, actually, there's a possibility, while the technology is evolving, there is a possibility to realize these things. And beside that, also, since the robot is very accurate and repeatable, then it is compared to human being, because human being, normally the accuracy of a hand cannot be sustained, and it is associated always with error. So having a robot to go to a specific place within the brain and inject a medicine is not easy to be done by a human being, but by a robot, because at least you have now robots accuracy reaching to 1 nano or 1 micron and below the 1 micron actually, then the damage caused to the brain will be very minimal compared to human beings actually. So as this general introduction about how the robotics field is evolving, and it's open actually, it's open ending. No one will actually can exactly know where we are heading exactly in the future. And because everything from my point of view, except the soul of human beings, anything beyond the God capability is possible to be done by human, because God is facilitating these things for human to learn and develop things and understand the surrounding. And facilitate, not just understand, facilitate what is available in the nature to support his or her life as a human being. So when we talk about bioinspiration and creative design, in the 21st century, the difficulties, actually the challenges is associated with the complex environment. Complex environment, especially when you're talking unstructured. You're talking to open space, not through the road. The roads still are, car roads are still manageable. But when you are going off roads in open area with rocks, sand, mud, so these are very complex operational environment that need to have a creative design and development to enable the robot to work freely and effectively within such environment. Also, the 21st century, the challenges within the 21st century is telling us or indicating there are a lot of problems or pressures facing human beings at the social life, as I said, for the elderly people and how to serve them economically and environmentally also. So there is a pressure actually caused by all of these things because we are developing a technology that affecting possibly negatively on the environment. So it's how to develop eco-friendly technology, whether it's for robots or for other mission-related tasks, to support such aim is to have a little impact on the environment, to have them sustainable. So the design should be sustainable and eco-friendly in general. So these need to be dealt with, and to deal with these things, it is required people to, which is when I say people, I mean mainly people working in the field, to be creative, to think out of the box, not to limit ourselves with the conventional aspects of design, to be native for new ideas, to be adaptable for any possible new information, knowledge, to adjust the design process, and to have the motivation and confidence in having effective thinking capabilities. And I'm always linking these things that saying conventional way cannot do that, cannot do the job. So who is going to do the job is that when you think about modifying or reusing already tested design, which is the conventional one, we cannot meet the requirement. And that's why we need to face new challenges. What is the new challenges aiming for is to design and solve new engineering and science problem that demand effective and agile solutions. Who is going to contribute to that? Conventional way, it will reach to a situation. So there should be another way of thinking, another way of creative approach to have to deal with this situation. I believe always, as a person working in mechatronics for the last 32 years, that mechatronics is introducing the solution, because mechatronics represent a philosophy more than a technique. Is a way of how to deal with the thinking aspects and with the development aspects, and how to integrate all of that together to develop new, to stimulate thinking and develop new ideas. So that's why, as a definition of the mechatronics, I'm just putting it in between, is regarded as a philosophy that is still stimulates synergy. Because always I believe, when you are defining mechatronics, I'm not calling it integration of different disciplines. No, I'm calling it synergy of knowledge from different disciplines, and that will support the design development. And such approach is featured by what? Interaction of open-ended interdisciplinary knowledge. There's no limit in mechatronics to stop at the knowledge, because it's open for all aspects of knowledge, as long as it is required to consider such a knowledge in biology, in chemistry, in electronics, in computer, in mechanical, in construction, whatever knowledge that is benefiting your thinking, to develop new ideas, you can adapt it actually as interactive knowledge requirement to reflect the interdisciplinary aspects of it. Building up a thinking skill through learning. And this is very important skill actually, because thinking is a skill that can be developed in a human being. And the mechatronics way of learning can establish such aspects of a skill. And we can have a skill in terms of creative thinking, and we can have a skill in terms of critical thinking. And both of these actually can be established and built up in our programs and have it actually developed in our student ability. Stimulate creativity and innovation, achieving best functional synergy. And this is a key point for mechatronics, because it has a concurrent design, then essentially the synergy in the design will not come individually at each section of the design, rather than it will start from the beginning of from the conceptual aspects of the design process and work together until reaching the target. So apply concurrent design methodologies, develop dynamic way of work supported by practical and communication skills. So mechatronics creative design use nature for the supporting the bioinspiration as a model of inspiration that will help to have a conscious abstraction of new principles from the nature, idea, methods, tools, inspiring creative design. And for what? To understand the condition and allow such approach to produce innovative bio-inspired design that help to transfer idea from nature to engineering. So the key principle for that, for the design principle in this case, help improving design process and find best possible solution for each design scenario. Now, when you come to there's two aspects, in the literature, you may see people calling the bio-inspiration as a biomimetics because they started with this word. Personally, I prefer to use the bio-inspiration because biomimetics is to coin, to duplicate things. Bio-inspiration, it may include the duplication, but it may include only to abstract idea and knowledge from the nature, not necessarily to duplicate it, rather than abstract different algorithms, different material, structures, etc. So, and accordingly, we can define the biomimetics as an interdisciplinary scientific research field characterized by technology outcome, which is normally related to hardware development and software development, not limited to hardware. So it is reflected in all different fields, as I mentioned: biology, physics, chemistry, information data analysis, data science, and nowadays we are having the big aspects actually of a data science, where a big data now is coming in and need to be processed carefully and effectively, supported by different learning algorithms or techniques. So bio-inspired design reflects interdisciplinary synergy. And the aim here, when you are talking about nature as a model and thinking about the bio-inspired design, we are actually considering the aim of that to achieve sustainability. And sustainability in terms of environment and resources. And this actually, the aim of to achieve sustainability will lead us to the development of sustainable design principles. So that's why bio-inspiration is the solution actually for a lot of problems in the coming future, especially when you are dealing with environment and resource. And actually, I'm working with the two colleagues from Austria and the UK in having a joint book about eco-mechatronics. Is how to consider actually environment, resources, and developing new technology that is not going to harm the environment. So the point here is not only developing a technology, it's to develop a technology that is sustainable without adding harms or more harms to the environment. So nature as a model is guiding to source knowledge and inspiration and help addressing sustainability and applying it in the development and practice of sustainable design. And this need to establish actually at the educational level, at the researcher level, a sustainable design thinking. Biomimetics, a concept, I will just go through it quickly. Help conscious abstraction of a new principle, foster innovative design, find out new techniques and functionality, seek new paradigms, develop a new material, actuators, sensors, design a new stream of intelligent machines. So we have different level of the bio-inspiration. You may abstract aspects from nature. You may develop new appearance, shapes, structure, and this happened for the sea submarines, cars, airplanes. So all of these actually been abstracted from the nature, from different animals, different structures, etc. Mobility at different beings living in our nature. Intelligent operation, thinking, decision-making, sensing capability, control, brain and decision-making, reasoning, formation, when you are dealing with a not a single entity, but multiple entity working together to achieve the target, and speech and understand, which is this is actually coming as a very hot topic nowadays. When speech and there's a natural language interaction, which is related to the human-machine interaction, and that is essential. Will actually bring us outside from programming a robot to do a task, rather than you can interact with the robot through the natural language, and the robot will understand what you want and learn, and then can do the work accordingly. So all of the mentioned technology that contributes to the progress of biometrics are highly interrelated and heavily synergized. And these are examples actually of at the structure level, the shapes, the material, at the mechanism level, behavior level, sensors and communication, and generational biomimicry. So you have a different example here showing that how up to now actually people consider the nature as a model to develop varieties of things. This is an example that's very attractive, because if you see in the nature, there is no motor rotating. All of the actuators are not rotating in the nature, but artificially we are developing an actuator that is rotating. So the alternative, all the animals, and they have muscles. And people start to think about developing artificial muscles, mimicking human muscles, at least at the beginning. And the performance of the natural muscles for human is stated in line 1, where here the strain, actuation, pressure, density, efficiency, etc. And there are different techniques being used to develop things. Electromagnetic, you have some deficiencies in covering it, but the best development here, according to Stable, is the dielectric elastomers. That is almost mimicking human muscle. But does that mean that it will be the best to replace every application? The answer no, because some of the application you need to have a very high torque, and you may use some of the currently available actuators for this purpose. But if you want to have a more flexible, effective way to conduct, then our human being is very, when you're moving our body, moving our arms through the muscles, very smooth and accurate. This is actually how using different types of muscle, and you can move this diaphragm in the way that you. This is the electroactive polymer type of actuators. Now, coming to the second point quickly, seems the time is running. So robot intelligence, the need for intelligence what? To enable a robot to interact and cope with the operational and task environment, to support reliable and effective execution of an assigned task, assess successfully conclude the final result and assure safety, exhibit emergence property. And this normally because through the intelligence, a robot can learn and add a new knowledge, a new experience, and not limiting itself to the previous functionality. It will add at the top of that with emergence capability that is coming through the experience and the interaction and conducting any given task. So why the robot needs sensors? These are a key element actually of intelligence. Without sensors, neither human being, neither any species actually can have an intelligent action. So through the sensor, whether it's a sensor as proximity or sensor with diversity, all of them are essential to have it, to build up the experience, to enhance reasoning through the data that's being collected, and to have a proper decision making, and achieving not just the decision making, also to follow up the action being taken, assure the accuracy, the efficiency, and the safety of these actions. So that's why the robot needs sensing for the purpose of task itself, to execute it, and it needs sensors to cover the need when the robot moving in the task environment, and it needs to have sensor to sense the robot internal structure as a configuration and its relation to the surrounding when there is interaction with the surrounding. The question may be raised actually, what kind of information the robot can collect and how to deal with these information, the meaning that how to abstract information from it to represent it, and this can be used in reasoning and decision making. So collect information, it is not yet, we are at the level of the sensing. Then we need to conduct perception, and perception normally is going to represent the knowledge or to abstract knowledge from these general information. And once you have this knowledge, then you can actually conduct cognition or reasoning, and then that will help to support learning and also to support proper decision making. So that's how flexible also when you are taking the action will be related to the locomotion of the robot, both at the task level and at the relocation of the robot itself while moving from one place to the other. How to assess the action performance is also another important fact, not just to enable the robot to move, but also to assess whether the action taken by the robot is correct or not, or whether the performance is very good or less than that. And also to learn through experience. This is a very critical thing. Not to repeat same thing every time, but if the robot is making a mistake, it should make use of that to recover and adjust itself and learn from it and have a better circumstances when conducting the same task later on. How to analyze and aware about robots' current state situation, forecast or expect future events. How to interact with other human or robots, because the robot is not going to be living alone. It's always going to work either with a human nearby or with other robots. So how to interact with other robots, communicate, coordinate, including human beings. Now, the main challenge facing intelligent robotics arise from the following issues. The difficulties of the environment working in it, which is incomplete or uncertain knowledge. The environment are often dynamic, unpredictable, changing. Sensor has the limitation normally. They are not always associated with noise and always associated with a certain range. The dynamic performance also of a sensor in terms of time requirement to function is critical. So we should consider actually when you're selecting a sensor for a job to consider the limitation associated with each individual sensor. So imperfect actuators also with the mechanical structure is adding to the imperfections of the performance. The development actually try to minimize that, but there are still how to deal with them through the learning process, and the perceptual events is a critical element. Also, as to deal with real-time actions, you need to assure two things: to have proper, accurate, reliable decision-making and that's going to be realized in the physical environment, is to assure that the decision being taken is correct and it's going to be done within the required time. Because having a just accurate decision is not critical, because if you have a plane that's going to crash, taking the decision what kind of problem is there is good, is needed, but it should be done before crashing. Otherwise, if the computer concluding the decision after the crashing, it will be meaningless for that decision anymore. So it is essential to couple sensing and action. And here is the extension, actually. That's why we should not limit the robot to our sensing capabilities, because we have a deficit in our sensing capabilities that the technology can actually overcome it, or the limitation that we have it in our sensing capabilities. The development of new sensors can substitute that limitation. And here, if you look at the electromagnetic spectrum, our capability is limited by this, this is normally within this wavelength of the visible spectrum. So we are actually only can see within this zone. All of the surrounding we cannot. So how to actually develop the capability to reach to all of these surrounding within the electromagnetic spectrum is here the development of new sensors is essential actually to cover that. Key issue associated with intelligence, mainly when you're talking about robot architecture as a physical structure, we should have a robust framework to support skill integration, should be modular and distributed integration, capability to facilitate adding or removing new modules, support different level of competence, and enable effective coordination of robot sensing and actions in real time. How about key software capabilities essential for intelligent robots? So here is control and execution of action, evaluate the outcome, quality of actions, navigate, avoid obstacle in real time and in dynamic environment, task decomposition, and interpret task description, requirement, goals, and targets quality, motion and activity planning, extract and build representation, aware of situation, the surrounding of whether about the mission environment or people or robot around, or the danger possibly surrounding the robot itself. Learn and reason with cognition capability and apply the learned skill. Safely interact with object human. Develop tools, practices, and standards that support, accelerate, and enable better robot performance. Besides that, as I mentioned earlier, which is a hot topic nowadays to support human-robot interaction or human-machine interaction, is to have a understanding at the machine side or at the robot side, the natural language, and here you can facilitate the communication. Plus, also for a personal robot, you need to have some affection, reflection from the robot to human, and then to have a better feeling for a human when you are interacting with the robot. Cognition normally is a prerequisite of adaptability that's going to enhance performance in real time. It helps tuning perceptual process to meet the desired motor activities, because exactly it's coming between the perception and the action, the cognition. And it represents essential requirement for evolution of intelligence, and it helps use the developed knowledge. I have a book, actually, editing a book, a new book called Cognitive Robotics, which is it's open actually for contribution for those who are interested to contribute with their research activity as a chapter in this book. This is still in the early stage of the process. dealing with the human and robot autonomy. Normally, human is fully autonomous entity, but who is binding us actually from acting improperly is the responsibility. So if you are a driver, you can drive your car and hit any things. But who is stopping you from hitting these things, whether it's a wall or a human being or a shop or anything else, is the responsibility. But when you are coming to the robot, actually, such responsibility is not there. So it has a different legislation dealing with that. That's why when you are dealing with the autonomous cars, we have 5 levels, but still we are almost in the 3rd level with the difficulties in developing a legislation that allow such levels to grow to and reach to the 5th level. While the technology researcher already developed fully autonomous car, but you cannot avoid accident out of that, and hence the legislation is essential. When coming to talk about autonomy at the robot side, it is a central factor determining the effectiveness of human-machine system. Therefore, understanding robot autonomy is essential to understand human. And remember here, when you're talking about autonomy, there are 2 aspects of it. Autonomy is going to support selfishness. And when you are asking a robot to cooperate, we are going to reduce the selfishness because we need to extend help or support to the others. So it's how to balance actually between as a human being, how to balance the level of autonomy and the cooperation requirement for a certain task. And this is actually a critical issue that should be balanced. So why autonomy? Many places are not accessible by human beings, either because of oxygen, for example, not available, very high temperature, very high pressure. All of that aspects actually may affect or have a radiation that a robot cannot, that a human being cannot reach these spaces. So it needs to send a robot, and the robot should have some level of autonomy to deal with the circumstances facing it. Non-deterministic, that interaction dynamic and open environment can neither be formulated completely beforehand, nor designed or analyzed using stationary or static models. So it is a dynamic model by itself. That's why adaptive or adaptable behaviors are required in development, plus not just to pre-wire these behavior, rather than to have a dynamic, evolving behavior being established during the learning process within such an environment. Dynamic change happening as the decisions are made, because when the robot is taking action, there is a change in the environment due to that action accordingly. The environment in which the robot is living is completely a continuous and not discrete environment. And also, when you are dealing with the robot, we should not deal at the module level. A robot is a complete entity, and the modules are integrated to reflect this entity. So that's why the integration of all entities should be considered properly to reflect the final behavior or the action or the performance of the robot itself. Autonomy requires what is going to require. They require that robots not only able to control themselves, their motion based on the sensor information, but they're required to react to unexpected events, change course if necessary, capable to learn from their experience, capable to consider and coordinate multiple conflicting objectives, and able to overcome errors in perception and action. Do we need to mimic human autonomy? The answer is no, sure. Because we go back to the law of robotics, robot should obey human being without being conflicted with higher order of a law. I mean, without follow human being when asking a robot to kill another human. So when the robot is going to be out of control, then it is a human being cannot be involved anymore, because it's going to be completely autonomous and will decide by itself what it's going to do. And that is normally human being is not willing, neither humanity is actually willing to have such robots. And there was a movie on that actually, I believe you remember. So technical constraints should be considered, legal and ethical constraints, information space representation, all of that will be put together. Robot autonomy and research need to develop qualitative learning, qualitative reasoning, qualitative behavioral adaptation. Robot autonomy should be bounded by ethics. Robot coherent intelligence should emerge from robot components, not all components. Yeah, I'm going to conclude.
Time is only 2 minutes left.
Yeah, I'm going to conclude. Develop effective model while interacting. Because I want just to go to this. These are the main challenges in robotic development, actually. I'm grouping it quickly. In the social interaction, we have human-robot interaction, robot-robot interaction, brain-robot, computer interface, affection. At the level of medical robots, you have higher level of autonomy, different size, scale, and purpose, micro, nano-robot, safety, because when you're dealing with medical robot, the safety is very critical and high level of consideration. Sustaining power source for any autonomous robot should sustain a power source to enable it to move without being bounded. And here is the things about power harvesting, lower power consumption, battery, better battery technology, bio-inspired and bio-hybrid robots use nature as a model, integrate and sustain living organ with the robot structure. Learning in real time, AI and machine learning supported by integrative learning techniques. Nowadays, you have the machine learning in different aspects. Perception, model-based reasoning, cognition, understanding natural language, multi-robotic agents, support cooperation, coordination, communication, real-time navigation with support of effective avoidance, mapping, cooperative mapping, localization planning, cooperative planning, robot autonomy and cognition, ethics and security, new materials, because you need to have new materials for both structure and the sensors and the actuators, control architecture, distributed, modularized, adaptable, flexible, eco design, and sustainable. Thank you very much.
Thank you very much, Professor Habib. So because of a very strict time in our conference.
Sorry for that.
No problem. This is very interesting topics. I think audience still can ask some question if they still curious about that. I would like to invite them to directly, probably next time, to message you via your email, for example. Once again,
okay.
Thank you very much for your...
Thank you very much. For those who would like to follow up questions, I will write my email.
Yes, please let the committee knows, and then we will distribute to all the
Yeah. I would be glad to reply to them.
Thank you very much, Professor. And once again, we send our regards from Indonesia, from Bandung.
Thank you very much.
Safe. Thank you.
Thank you. Take care.
Take care for you all.
Thank you very much.
At this very moment, we would like to express our deep appreciation for today's keynote speakers, Professor Katupitia and Professor Habib, for delivering us such important and insightful talks. We are very honored to have you both in Morse 2021 today. And for the moderators of the talk, thank you so much for your service. Dear all conference participants, in few moments, we are going to join the parallel sessions. For all presenters, please join the assigned breakout rooms for your preparations. And for other participants, you may join the parallel session, which are available in 2 breakout rooms. Should any technical difficulties, please kindly ask the morse 2021 help desk for your help.
All participants, we will continue our program, the parallel session, in 5 minutes. And then please take your free time for 5 minutes, and we will meet again in this room in 5 minutes, and you can directly go to any room that you want to follow. Thank you.